Part C. Figure 5.2 illustrates the structure and dimensions of a carbon nanotube of circular cross-section and diameter 1.2 nanometers and length 80 micrometers. So you can see the length of it's 80 micrometers and its cross-sectional diameter is 1.2 nanometers. Given the Young modulus for a nanotube is 1.1 by 10 to the 12 pascals, calculate the tensile force which will cause a 0.15 micrometer increase in the length of this nanotube. So we're going to write down what we know here. We know that the extension x is equal to 0.15 10 to the minus 6 meters. We know that the length is 80 by 10 to the minus 6 meters. We know that the Young modulus for the material is 1.1 by 10 to the 12. And we have enough information to get a cross-sectional area. So it's pi times r is 1.2 divided by 2, so it's 0.6 by 10 to the minus 9 squared. So you've got all your information there. All you need to do is calculate E is equal to stress over strain. Stress is force over area, and strain is extension over length. When you divide by a fraction, it's the same as multiplying by it upside down, so that becomes F times L over A times X. And so when you put all your numbers in, we're looking for F, so we're going to rearrange that. So F is therefore equal to E times AX over L. So now we're going to put all our numbers in. So F is equal to, E is 1.1 by 10 to the 12. Length is 80 by 10 to the minus 6. X is 0.15 by 10. Sorry, that's the wrong way round. I shouldn't have put the length in there. I'd put X in there by 10 to the minus 6. And the area is the pi times 0.6 by 10 to the minus 9 squared. And then the length is in the bottom, and the length is 80 by 10 to the minus 6. There's an awful lot of numbers there and an awful lot of standard form going on, so you just have to be careful about it. And when you do that calculation, you get 2 by 10 to the minus 9 newtons is your answer. Calculate the strain energy in the nanotube when stretched by 0.15 micrometers. Assume the nanotube obeys Hooke's law. So you know that energy in a spring or in a nanotube, in this case, is given by half F times the extension. And so that's a half times 2 by 10 to the minus 9 times the extension up here was 0.15 by 10 to the minus 6 meters. And that gives you 1.7 by 10 to the minus 16 joules. Part D. Graphite is a good electrical conductor under normal circumstances. An experiment was performed to see if it obeys Ohm's law. The data was collected using this circuit, so a typical circuit with a variable resistor and 2 meters in it. The voltage current characteristic of a graphite rod is given. On the circuit diagram, label the milliammeter and the millivoltmeter, so the ammeters in series and the voltmeters in parallel. Explain how this confirms that graphite is an ohmic conductor, as it is a straight line which goes through the origin. Then V is proportional to I. And then the last part, graphite has a resistivity of 7.8 by 10 to the minus 6 charge carrier density. So we'll just write that down. Resistivity 7.8 by 10 to the minus 6. Charge carrier density N is equal to 1.1 by 10 to the 29. We're looking for drift speed, so we're looking for V. In a sample of graphite, length is 80 millimeters and the voltage is 26 millivolts. So what we need there is, we're going to use I is equal to NAVE. First of all, we're going to calculate, just going to do this separately. I'm first of all going to calculate the resistance using rho is equal to RL over A. See, I've done that the wrong way around. I'm going to do it this way. R is equal to rho L over A. and that's equal to 7.8 by 10 to the minus 6 times 80 by 10 to the minus 3. And then A, that's our calculation from a way back in part C of the question. If I just go back here, the area here, there's the area there, pi by 0.6 by 10 to the minus 9 squared, that's it there. So it's pi by 0.6 by 10 to the minus 9 squared. And the resistance comes out as 5.5 by 10 to the 11 ohms. So we've got resistance, and now we can calculate current. So I is equal to V over R. I could have done all of this in this equation, but there's an awful lot of numbers, an awful lot of working out. You're probably better to do it separately. So I is equal to V over R, and V is 26 millivolts, and R is 5.5 by 10 to the 11. And that comes out as a very tiny number, 4.7 by 10 to the minus 14. Now that's not very surprising, because you're talking about you're talking about graphite there, so the current's very, very small. That's amps. And then the last part of the question, the electron drift speed. So we're looking for V is equal to I over N A E, and that's 4.7 by 10 to the minus 14 amps, divided by N, which is 1.1 by 10 to the 29, multiplied by A was your pi by 0.6 by 10 to the minus 9 squared again, and then by 1.6 by 10 to the minus 19. And that answer comes out as 2.36 by 10 to the minus 6 meters per second.